Welcome to The Explainer. Today, we're diving into a beautifully simple scientific law that, believe it or not, is working all around you, from life-saving medical tests to making sure your favorite beer tastes just right. Let's jump in. So, how is this even possible? I mean, really, how can a beam of light tell us exactly what's floating around in our water and even how much of it there is? It sounds kind of like magic, but it's really more like a detective story, and the main clue is light itself.
Here's how we're going to break it all down. First, we'll start with this simple idea of color. Then we'll crack the code, the actual equation that turns that color into hard data. After that, we'll explore the logic behind why it works, see it in action in the real world, and finally, really get why this law is such a big deal.
All right, so our whole investigation starts with something you've definitely seen before. When you dissolve something in a liquid, it changes the color, right? The more you add, the darker and deeper that color gets. But the real question is, how do you go from just looking at it to getting a precise scientific measurement?
Well, here's the fundamental idea. Just imagine that all the molecules in a solution are like tiny little obstacles. The more obstacles you have, the harder it is for light to get through from one side to the other. So by measuring the amount of light that gets blocked, we can pretty much count the molecules that are in its way. Simple as that.
Now, to turn that idea into something we can actually use, scientists came up with this really elegant and surprisingly powerful equation. So let's take a look at the code they cracked. And here it is, the Beer-Lambert law. It looks super simple, right? A equals epsilon CL. But don't let that fool you. Every single part of this little code tells a crucial piece of the story. So let's break it down, one variable at a time. Okay, first up is A for absorbance. This is what we're actually measuring. An instrument called a spectrophotometer shines a light through our sample and basically counts how much of that light doesn't make it to the other side. So a higher absorbance just means more light got blocked.
Next, we've got this Greek letter epsilon. It stands for molar absorptivity. Now you can think of this as a substance's unique fingerprint. See, every chemical absorbs light a little differently because of its unique molecular structure. The electrons in a molecule can only grab photons of very specific energies, which correspond to specific colors of light. This is what lets us identify exactly what we're looking at.
Then there's C for concentration. Now, this is usually the big mystery we're trying to solve. This is the how much. How much pollutant is in the lake? How much iron is in a patient's blood? This is almost always the unknown we're hunting for.
And finally, we have L for path length. And you know what? This one is super straightforward. It's just the distance the light has to travel through our sample. We keep this constant by using these standardized little containers, usually exactly 1 centimeter wide, which makes all the math really nice and easy.
And this analogy just illustrates the whole idea perfectly. Think about it. A low-concentration solution, it's like a sparse forest with trees spread way out. It's easy for light to find a path through. But a high-concentration solution, that's like a super dense, dark forest. Very little light is going to make it all the way through to the other side. More trees, or in our case, more molecules, are there to block the way.
Okay, the formula is cool. It connects all these ideas. But what's the actual logic here? I mean, why does this relationship even work in the first place? Well, it's actually really intuitive when you think about what's happening to that single beam of light on its journey.
Imagine that light traveling through the liquid, layer by tiny layer. The very first layer of molecules absorbs a certain percentage of the light. Now, the light that gets through is a little bit weaker. The next layer then absorbs that same percentage of the now weaker light, making it weaker still. This compounding effect creates what's called an exponential drop in the light's intensity. And that is precisely what the Beer-Lambert law so elegantly describes.
Now here's the most important part. This isn't just some neat theory you find in a chemistry textbook. No way. This law is an absolute workhorse out in the real world, solving critical problems that affect our health, our planet, and yeah, even the quality of our drinks.
Just look at this range. It's incredible. You know that little clip they put on your finger at the hospital? That's a pulse oximeter. It's using the Beer-Lambert law. It shines red and infrared light through your finger to literally measure the color of your blood, which tells doctors your oxygen levels. It's used to test our water for pollutants, to make sure beer has the right color and bitterness, and even to figure out how much DNA is in a sample at a crime scene. Now, of course, it's not perfect. It works best in clear solutions that aren't too concentrated, but its versatility is just amazing. So let's just zoom out for a second and appreciate the huge impact of this one little equation. It's like a bridge. It connects the world we can see, the world of color, to the invisible, microscopic world of molecules and their concentrations.
Get a load of this number. Over 300 million. That is a very conservative guess for how many clinical blood tests are done every single year in the US alone that rely on this very principle. We're talking hundreds of millions of decisions about people's health, all guided by the simple idea of light being absorbed.
And this quote just says it all, doesn't it? That's the real genius here. It takes something we can all see with our own eyes, a liquid getting darker, and it transforms that simple observation into hard, reliable data that we can use to make life-changing decisions.
So in the end, the Beer-Lambert law gives us this incredibly powerful lens to peek into the molecular world. And it leaves us with this really tantalizing question. As our technology gets better and better at detecting light, what other secrets are just waiting out there to be discovered, if only we knew the right color to look for?